Okay, so we'll discuss complex numbers and their properties. And the theory of complex numbers is very interesting and it has lots of applications, right? But and in our course we'll try to learn only basic properties of complex numbers. That means what we learn, uh, addition, multiplication, division or basic properties, and where various inequalities, equalities, log of complex numbers.
Sir, will we go ahead of what we learned in our 11th and 12th, or is it the same level?
What we learn in 11, 12?
Basic all these properties only, the addition, multiplication, and square root of unity, and polar coordinates.
So did you learn nth root of complex numbers?
No, sir.
Yes. Did you learn nth root of complex numbers?
No, sir.
So we learn this log of complex number.
Again, no.
Now regions in complex plane. Right? And in comparison with regions in Cartesian plane. Right. And various inequalities. And inequalities. Right. And first of all, we'll try to introduce complex numbers in different way. Okay, so recall this. What is set of real numbers? So we denote it by R. And what is it? Rationals union irrationals, right? Rationals union irrationals. So what are rationals? Rationals, set of rational numbers is P by Q. P and Q are integers. Q is non-zero, right? This is a set of rational numbers. And what is irrational? The real numbers which do not satisfy properties of rationals are called as irrational numbers. And how people came to know about key? See, as I told you before, initially people believed that key. Uh, uh, Initially people had natural number, then integers, and then they found that key rational numbers are there. And people believed that key rational numbers are sufficient, that will fill up the line completely. Real line, rational numbers will fill up this line completely. The people believed this. And then people found that, ancient mathematician found that there is a sequence. There is a sequence xn of rational numbers. There is a sequence xn of rational numbers, uh, which converges to a number alpha, and alpha is not in rational numbers. Do you understand this meaning of this sentence? Do you understand meaning of this sentence?
Yes, sir.
Right. And do you know the now question I would like to ask? Does there exist a sequence? Does there exist a sequence of rational numbers which converges to root 2? Do you know such sequence? You have already learned this in calculus. Yes. Second, does there exist a sequence xn of rational numbers which converges to irrational number e? What is your answer of these two questions? What is your answer? Okay, the second question. What is the answer of second question? Does there exist a sequence of rational numbers which converges to e? Yes, do you know answer of this question? Yes or no? Yes. Can you hear me?
Yes, sir.
Now, what is the answer of the question? You don't know answer or you know answer? If you don't know, you should tell me. We don't know answer. Then I will tell you.
Sir, I think the answer for second is 1 plus 1 upon n raised to n. It converges to e.
Right, very good. 1 plus 1 by n raised to n. And limit of this sequence is e, that you have already learned. But e is irrational number. Why? That you should read. Why? But e is a rational number. But what is the sequence? What is x1? 1 plus 1 by 1 by 1 raised to 1. What is x2? 1 plus 1 by 2 raised to 2. Right. X1. Is x1 rational number? Is x2 rational number? Yes. Am I right?
Yes, sir, all the terms are rational.
Each xn is rational, but it converges to a number which is not rational. Right? Now, can you find a sequence of rational numbers which converges to root 2? And you have already learned this in calculus. X1 is equal to 1, xn plus 1 is 1 by 2, xn plus 2 upon xn. And you have proved that this is a monotonic increasing and bounded above, so it converges to. So limit of this is root 2. Have you learned this? Yes. Do you remember this, or you just later on you check your notes, you will find it. And if you replace any number here by a, then it converges to root a positive number. So such sequence, and this is a sequence of rational numbers which converges to root 2. So the point is only rational numbers are not sufficient. People found that there are sequences of rational numbers which converges to a number which is not rational, and people decided that some numbers are missing. Some numbers are missing from this line. Only rational numbers are not sufficient to fill up the line, and these missing numbers they call as irrational numbers, and then line is completely filled. Right? Initially there were gaps called as Dedekind cuts. Right, so Richard Dedekind was a mathematician and he found that there are cuts. Only rational numbers will not fill up the line. And in that way, the system of real numbers becomes perfect and complete. Right? What are the properties? Basic property of real numbers is order property. And completeness property. And so these two properties are main properties of all field axioms are there. Right. What are the field axioms or algebraic properties? Right. Do you remember these words? Do you remember these words? Yes. Field axioms are order properties of real numbers. Do you remember these words? Yes or no? Order properties. What are order properties? What are completeness property? What is a completeness property of real numbers? Correct. Now, as a consequence of all these properties, there are certain properties. Right. What are the properties of real numbers? A into B is equal to 0 implies A is equal to 0 or B is equal to 0. Right. A into B is greater than 0 if and only if either both are positive or both are negative. Correct. Product of two real numbers is negative if and only if one is positive and another is negative, or A is negative and B is positive. So similar to these properties, one important property is key for every A belongs to R. If A is not equal to 0, then A square is positive. Right, square of every non-zero real number is positive. This is the main point for us now. Right. So therefore, if f of x is equal to x square plus 1, this polynomial, right, is polynomial in Rx. Is it polynomial in Rx? Am I right?
Yes, sir.
Yes, sir. Now, but its roots, then its roots are not in real numbers. Right? Its roots are not in real numbers. Why? Because if alpha is a root of fx, then what will happen? Alpha square plus 1 is equal to 0. Am I right? That means alpha square is equal to minus 1, which is negative. So alpha square is square of some number which is negative, and therefore what we can conclude from that, is alpha real number? Is alpha real number now?
No.
No, because basic property of real number is square is always positive if it is non-zero. Certainly it is non-zero, so therefore alpha is certainly not a real number. Right. So therefore alpha, which is actually square root of minus 1, called as imaginary number. It is not real. Right, not real, hence it is called as an imaginary number. Right, so alpha is equal to square root of -1 is called as an imaginary number. So we denote for convention, so or for simplicity, the notation we denote square root of -1 by a symbol I. Therefore, I is equal to square root of -1 and hence I square is equal to -1. This is what the symbol we denote alpha. Now, as like real numbers, we know we arrange all the real numbers on the line and we can identify here is additive identity. Numbers on the right side of 0 are positive, numbers on the left side are negative, and if x is on right side of y, then x is greater than y. X is greater than y means on real line x is on right side of y. On all these things we know about real number. So similarly, how to visualize complex numbers? So I, which is square root of -1, is identified by a point 0, 1 on y-axis of the xy plane. Right, because to understand this number system, we need to understand this by some set. So we can identify these points by points in plane. Right. So therefore, some k times I, or what I should say here, t times I times I, and what is t? T belongs to R. Are identified with are identified with 0, t. Right. So so this is real line, and to locate complex numbers in a plane, we should go outside the line, real line. So I is identified with this, then 2i, then 3i, then 1.5i here, or all you vary real numbers, you will get corresponding complex numbers. So every any point AB in plane R2 is identified by which complex number? So AB. Okay, now what is this 1? But as a part of plane, it is 1, 0, right? As a part of plane, it is 1, 0. So 2, 0. Therefore, AB, I can write it as 1, 0 plus 0, 1 times B. Am I right? Whatever I have written is correct. Is it clear whatever I have written? I root -1 is identified with 0, 1, right? So Ti is identified with 0, t, right? Then 1, 0 in complex plane, it is identified with 1 or 1, whatever is in opposite way. So 1, where is 1 on real line is identified with 1, 0, right? And therefore any t is identified with t, 0, right? And now you look at any point in the plane. What is it? A into 1, 0 plus b into 0, 1. Am I right? Is it correct?
Yes, sir.
Okay. Now 1, 0 is identified by 1. So A plus b, and 0, 1 is identified by what? b into 0, 1
I.
I, and therefore an ordered pair AB in a plane R2 is identified with the complex number a plus bi, right? And when we say complex number 2, 3, then it is 2 plus 3i, because our identification 0, 1 is I. That is what the basic identification. We locate that point on the y-axis. So this is how we define the set of all complex numbers is denoted by this symbol C, right? And what is this set? X plus iy, where x and y are real numbers and I square is -1. This is a property of I. This is a set of complex numbers. Now, but when we say that it is a set, then what are the properties? How to multiply, how to add? So for z1 is equal to a plus bi and z2 is equal to c plus di, z1 plus z2, how do we add? So z1 plus z2, so if you look at a comma b is identified with a plus bi, and c comma d is identified by c plus di. And how do we add two vectors as a vector in R2? So similarly we are going to add these two as a plus bi, c plus di is a plus c plus I times b plus d. In this way we are adding two vectors. So the addition is like addition of two complex numbers. So if one complex number is here, a plus bi means actually it is location of point AB, and c plus di, that means it is actually point CD. Now how do we add two vectors, right? So this is what? AB plus CD, correct? This is the addition of two complex numbers. Or okay, note before this, if a plus bi belongs to set of complex numbers, then a is called as real part, real part of z, and b is called as imaginary of z. So real part means it corresponds to the component on axis. So real axis. So this axis is called as a real axis, and in complex plane this is called as a complex axis, right? And with this identification, this plane is called as a complex plane. This is called as a complex plane, and therefore every real number itself is a complex number, because if you look at 2, right, if you look at 2 itself is 2 plus 0i. 2 plus 0i means it corresponds to 2 comma 0. So imaginary part is 0, right? So real part of z, imaginary part of z.
Sir,
Yes.
So can we like you added the complex numbers according to the vector addition rule, etc., etc. So can we treat complex numbers like vectors?
Yes, but then the big basic question is what are vectors? Right? And the real numbers also can be treated as a vectors. Polynomials also can be treated as a vectors. Right? So this is my first question. What is the space of vectors? Which is called as a vector space. Right? These are the very fundamental questions, and anything in the universe can be treated as a vector. Right? All air particles can be treated as vectors. Right? Every planet in the space can be treated as a vector. Right? Every real number can be treated as a vector. So vectors is a very general abstract concept, and therefore there is a separate branch of mathematics or subject called as linear algebra. Right? And in SY BSc you will learn this course, linear algebra, and this course talks about what is a general vector space and what is the meaning of vectors, general meaning. Right? And if you are curious, after your first year exams over, you can read this book of linear algebra. Right, in second year BSc you will learn this, and why this course subject is there, because it has lots and lots, many applications in computer science and every field of science. Right, and while talking about functions, I talk about functions like f of x plus y is equal to fx plus fy. We discussed such type of functions. Do you remember?
Yes, sir, linear functions.
So this function is called as a linear. That means things happens linearly, and vectors are something called as a linear objects. Right. So this mathematics, uh, if you want to understand universe, you need to understand mathematics. And how to understand? This is a way. We are learning some simple ideas, things right now, and you have to explore these ideas and try to learn in more abstract manner, and then see how these things are used to solve real life problems. So therefore vector is a very general concept, abstract. Whatever you learned so far, it was just mechanical thinking. Let us call this as 1 comma 2 as a vector and 3 comma 5 as a vector and add them. So you learn this kind of things. This is very elementary and mechanical thing, which is not of use as such, right? Because you don't know what is the meaning of 1 comma 2, right? So what is the meaning of 1 and 2 in case of vector? If you are looking at vector u1 comma 2. So what basically it says ki 1 into 1 comma 0 plus 2 into 0 comma 1. And if you look at the plane R2, 1 comma 0 is here, 0 comma 1 is here, and their combination with two scalars 1 and 2, that gives you vector 1 comma 2. Right, and therefore whatever vector you take in a plane, that can be expressed as a combination of these two basic vectors, and therefore these two vectors are very special vectors, 1 comma 0 and 0 comma. Whatever vector you select in a plane, you can express as a combination of these two vectors. And if you take a space of all polynomials, can we do same thing for polynomials? So there are several questions. If you take matrices, space of all matrices, can you do same thing for matrices? Given any matrix, can we express every matrix in a combination of some specific matrices? And this specific matrices plays an important role. Right. Anyway, so right now we are not interested in this thing, so we'll just uh, concentrate on our complex numbers. Okay, so real part, imaginary part. Now, how to multiply? So Z1 is equal to A plus BI and Z2 is equal to C plus DI. So how do we multiply Z1 into Z2? So Z1 into Z2 is A plus BI into C plus DI. Basically, the multiplication is defined in a specific way so that AC minus BD plus I times ED plus BC. Right, in that way this is defined, or ultimately what is AC minus BD comma AD plus BC. In that way this multiplication of AB and CD is defined. But in case of vector space, this multiplication is not possible actually. Right, you cannot multiply two vectors U and V. You have product, cross product, that is a different thing. Right, cross product is a different thing. You have dot product, that is again a different thing. But the multiplication defined here, it is a multiplication of two complex numbers. Correct? Now, if Z is equal to A, then what is a multiplicative inverse? Does it exist? Right, 1 upon A plus BI. And you must have done such kind of things. So multiply by conjugate and divide by conjugate. Right? What is it? A minus BI upon A square plus B square. Is it correct? Whatever I am writing is correct. This is 1 by Z or 1 upon A plus BI. So multiplicative inverse. So but this is possible. When we can find multiplicative inverse for 1 by Z? When it is possible? If A square plus B square is non-zero. A square plus B square is non-zero, that means if A is not 0 and A is not 0 or B is not 0. Correct? A square plus B square is non-zero if when it is possible or B is non-zero. Now note that complex number x plus iy is 0. When we say that complex number is 0, if and only if when we say that a complex number is 0, if its real part is 0 as well as imaginary part is 0. Therefore, complex number is not 0. What is a negation? If and only if x is not 0 or y is not 0. Right, its real part is not 0 or imaginary part. If one of them is non-zero, we say that complex number is non-zero. Because in complex plane, this is a 0, 0 complex number. Anything different from this is a non-zero complex number. Correct. And therefore, what is the conclusion from this? Therefore, for Z belongs to C, Z is equal to x plus iy, Z inverse or 1 by Z exists if when multiplicative inverse exists, if and only if Z is non-zero complex number. That is, for every Z not equal to 0, multiplicative inverse exists. Right? Now, next point, if Z is equal to x plus iy is a complex number, And therefore, what is z plus 0? Z plus 0 means x plus iy. And what is 0 complex number? 0 plus 0i. What is the sum? What is the addition of these two? What is the addition? Yes. Is it the same complex number? Right. And therefore, any complex number added with 0 complex number gives same. Therefore, 0, which is 0 plus I times 0, is additive identity. Correct? In set of complex numbers. This is additive identity. So, if z is equal to a plus bi and w is equal to minus a minus bi, then what is z plus w? Right, what is z? 0. And therefore, sum of these two complex numbers is 0. That means additive identity. Therefore, w, which is minus a minus bi, is additive inverse of a plus bi. Therefore, every complex number has additive inverse. That is clear. Now, if z is not equal to 0, therefore, if z is equal to a plus bi, that means a is not 0 or b is not 0. Therefore, z inverse. What is z inverse? A upon a square plus b square. That means a square plus b square is non-zero. Certainly non-zero if one of them is non-zero. So minus b upon a square plus b square I exists in the complex plane, and z into z inverse is 1. Am I right?
Yes, sir.
Right. So z into z inverse is 1. Before that, let me. Okay, this should be 6 and this should be 7 actually, because z is equal to x plus iy, and 1 is what? 1 is 1 plus 0i. Then what is z into w, or z into 1, or x plus iy into 1 plus 0i? What is the multiplication? Z. Therefore, 1 is multiplicative identity in set of complex numbers. So this is a multiplicative identity, and for every non-zero complex number there exists multiplicative inverse, so that product is multiplicative identity. Therefore, inverse exists. Therefore, if is non-zero, then z inverse exists. So multiplicative inverse exists, and other properties you can have is z1, z2, z3. If you take three complex numbers, then z1 into z1 plus z2 plus z3 is same as z1 plus z2 plus z3. z1 into z2 multiplied with z3 is same as z1 multiplied with product of z2 and z3. So what these two properties are called?
Associative.
Associativity. So associativity with respect to addition and multiplications are satisfied. That you can check easily, not difficult to check. Now if z1, z2 and z3 are complex numbers, then Z1 multiplied with Z2 plus Z3. So what you can say about this? Ki Z2 plus Z3 is Z1 into Z2 plus Z1 into Z3. So what this property is called?
Distributive.
Distributive property.
Distributive property. Right. Now do you understand all the properties of real numbers are set? Z1 into Z2 is same as Z2 into Z1. Z1 plus Z2 is same as Z2 plus Z1 for any complex numbers. Right. So all the properties which you studied for real numbers, algebraic properties or field axioms are satisfied with respect to this addition and multiplication. Correct? Yes. Is it clear?
Yes, sir.
Fine. So, and therefore, like real numbers, set of satisfies field axioms. Right. That is set of complex numbers is a field. Field means the set which satisfies all the properties. That means what is a field actually? There are two operations, addition and multiplication. Right. Two operations, addition and multiplication, and all these properties is called as a field. So set of complex numbers have all those properties. Those are for real numbers, basically field axioms. But there are some other properties of real numbers which are not satisfied by complex numbers. Right. So, but C is not an ordered field. So why then you think it about it later on? Right now it is not very essential.
Sir, can you
Yes.
please repeat the last few sentences? I wasn't able to hear it clearly.
So what is a field? Key two operations, addition and multiplication, and these above properties which you learn for real numbers and we discuss now. Okay, all these property, inverse identity, and so on. All these property, there are two operations on a set, and these properties are satisfied. All above properties is called as a field. So same properties are satisfied by real numbers, same properties are satisfied by rational numbers, same properties are satisfied by complex numbers. So such set is called as a field, right? So therefore set of complex numbers is a field, but it is not ordered field. And therefore, what are the additional properties of real number? Order properties and completeness property. So is not a complete ordered field. It is not a complete ordered field. So this order properties and completeness. So what is the use of order properties in case of real numbers? Why order properties are there for real numbers? There are certain questions. Why order properties for real numbers? Right, this is a basic question because of order properties we can compare which number is smaller and which number is larger, and so that we can define supremum and infimum. And because of supremum infimum, exists for every bounded set, it is complete. Set of real numbers is complete. Right. And therefore, on set of complex number, there is no order so that supremum, infimum, or completeness property satisfied. So there is no such order. Of course, there is an order on complex numbers, but that order is not consistent or is not useful. With respect to that order, this completeness property cannot be defined on complex numbers. Right. So that's why the real numbers on real line, then on this side it is smaller and on right side it is larger number. So in case of complex number, it is very difficult. So there is no order so that it will satisfy completeness property. That is the main point. But right now this is not important for us. We are just interested in algebra of complex numbers, not analysis. Yes. And maybe later on, while discussing practical questions, we'll discuss about this. What is the problem with complex numbers?
So, sir, this is like the a set of properties that we lose when we go from real numbers to complex numbers.
Yes. And what properties lose? The completeness property.
So,
Right.
can you elaborate a little bit on the order properties?
You learned this in calculus. Yes. What are the order properties?
Yes, sir, but not in that much detail.
Of real numbers. So there exists a set P or subset P of real numbers such that what property this set subset satisfies? For AB belongs to P, A plus B and A into B belongs to P, right? Second, for any A belongs to R, either exactly one of the following is true. So for any real number, either it is A belongs to P or A is not in P or A is equal to 0. So whatever real number you select, so this P is called as a set of positive real numbers. P is set of, the set P is called as set of positive real numbers. Right. And the set which satisfies this property is called as a positive real number. That means if X belongs to P, then we denote it by X greater than 0. This is a notation that X is in P. X, this is a symbol that X is in positive. So this is the order, these are the order properties. So the second one is called as a trichotomy property. So if you take two positive numbers, their sum is positive, product is positive. And if you choose any number, then either that number is positive or it is not positive or it is 0. So if X is not in P and X is not 0, then we say that, or we write it as X is negative. Such numbers are called as a negative or it is less than 0. Right. So therefore, if you take any number, either it is positive, negative or 0, this is called as a trichotomy property. Right. So you take any number, either it is positive, negative or 0, but not two at a time. And as more general, for A and B belongs to R, A minus B is a real number, and therefore by trichotomy property either A minus B is positive or A minus B is not in P, or A minus B is 0 or negative. That means it is same as A minus B is positive, or A minus B is negative, or A minus B is 0. It is same as A is greater than B, or A is less than B, or A is equal to B. This is what the more general form of order property or trichotomy property. So therefore, given any two real numbers, they are always comparable. Comparable means we can compare key, given any two real numbers, A is greater than B or B is greater than, or they are same. There is a comparison order, right? And this comparison helps. Otherwise, if there is no comparison, there is no order property. 1,000 rupees more than 500 rupees. Why? Because of order properties of real numbers, right? Is greater than 500. Why this is so? Otherwise, today we would have said 1,000 is greater than 5,000. Tomorrow I will say that no, 5,000 is 500 is greater than 1,000. So that would be changed. But these order properties are there. So definitely 1,000 is anytime it is greater than 500. So these are the order properties. And because of this comparison, we can define upper bound, lower bound, because we know which is smaller and which is larger. And then supremum and infimum, and every bounded set has supremum in real numbers or infimum in real numbers. So that is a completeness property, and that is because of this order properties. So therefore all these properties are complementary to each other.
So, sir, like in complex numbers, there is no concept of one number being greater than the other.
There is no
I mean, is there no concept of one number being greater than the other number? Like here in real numbers, we can say that A is greater than B or A is less than B. In complex numbers, we can't say that that A is greater, that a complex number is greater than another complex number, or it is less than another complex number.
no, it is not like that. Key order properties of, see, if you look at the completeness complete structure of real number, then as a symbolically algebraic properties, then order properties and completeness properties. So all these three things are complementary to each other, and this structure together is a complete order field, right? But in case of complex numbers, certainly there is order, but there is no completeness property with respect to that order, right? And what is the order? Dictionary order: A plus BI and C plus DI. Suppose you have two words A, B and CD. How will you compare two words in the dictionary? How will you compare two words? First, we'll look at first real part. So if this is my Z1 and this is my Z2, so Z1 is less than or equal to Z2. I want to compare two words. I am defining. I am comparing two words. So if A is less than C, or A is equal to C and B is less than or equal to D. How do we compare the words? First, we look for the first letter. If first letter is higher position, then we'll put the number at higher. Suppose first numbers are same. Apple and ant. So where is the position of this number, which is at higher position, which is at lower position? So then banana. In dictionary, how do we put the number, these words? First we compare the first letter, right? Now ant and banana. So ant is at higher position and banana is later, so it is at later. So which first? Suppose first letters are equal. They look at apple and ant. Then we'll go to the second letter. Do you understand this? Do you understand what I am saying? Yes.
Yes, sir.
What I am. So first we compare the real parts. If real part of first complex number is smaller and second complex number is larger, then that second complex number is larger, irrespective of whatever imaginary parts. But if real parts are equal, C actually here C. So if real parts are equal, if A is equal to C, then compare the imaginary parts. So that means in dictionary, if first letters are same, then compare the second letters. That order you can define, but that order is not useful for the completeness. And therefore there is no completeness property as such with respect to this order. Correct?
Sir, all the order properties that we define on the real numbers, uh, that followed by the complex number or not?
No, this is different thing. What order properties we have defined? Ki when A is less than B, if A minus B is positive in the set of positive, this is what we defined the order of the. In this way we compare two real numbers. When A is greater than B, if A minus B is positive, means A minus B is in the set of positive. In that way we have defined the order. In case of complex number, you cannot say that ki Z1 is less than Z2 as such. There is nothing. You read any complex number book, you will not find such symbol, less than, unless you are dealing with real numbers. Correct?
Yes, sir.
And what I told you, ki there is a order, dictionary like order, but that order is just order, not useful in the sense of supremum and infimum or kind of things, completeness.
And sir, what are the completeness properties?
What is in real numbers? You studied completeness properties. Did you study completeness property for real numbers?
No, sir, I don't know.
Yes, sir. Yes, sir. We just studied it as LUV action
Completeness
or supremum
property
property.
or LUV action. Completeness property or LUV axiom, right? What is it? Every non-empty subset of R which is bounded above has a supremum in R. Similarly, every non-empty subset of R which is bounded below has infimum in R. So if your set is subset of real numbers and it is non-empty, and if it is bounded above, that means it has one upper bound, at least one upper bound, then certainly supremum exists in real numbers. And why this is special? Because there are some sets like rational numbers. You can find a subset of rational numbers whose supremum is not in rationals. But in case of real numbers, once your set is bounded above, its supremum is exists in real numbers. If your set is bounded below, its infimum exists in real numbers. That is a completeness property of real numbers. Yes, is it clear?
Yes, sir.
Okay, so we'll discuss further properties of complex number next time. Tomorrow's lecture again 11 o'clock, right? So we'll stop here. Okay, so you read it carefully again, and it is not like 12th standard, you just study the complex numbers and their properties. So here we have to understand in some more general sense.